In this video, we're going to talk about the equilibrium constant and calculations specifically using homogeneous equilibrium. Now, if you want to go on to the slightly simpler version of equilibrium before you do this, because this is a more complicated calculation video, please go to module 3 and look at equilibrium first. Now, just a reminder of equilibrium, you can see here I've got concentrations and I've got time. And if I just walk across here, you can see that I've got concentration of NH3, H2 and N2. So hopefully you're bringing that together in your head and you can see that that is the Haber process. So N plus H2 goes to NH3. Now, NH3 is the product, so you can see it's coming from 0 and going up. And then the orange and the yellow are nitrogen and hydrogen, and they're coming down as the product is coming up. So I've got a line here, and I just want you to tell me, what do you think that line means? Obviously, you can't tell me on a video. But think about it. What does it mean? What it means is the concentrations are staying at the same. They're the same. And that must mean that the forward and backward reaction rates in this reversible reaction are going to be the same, which means this must be equilibrium. So this is what we're going to be talking about today in terms of calculations mainly. So just to remind you though, what is your definition of equilibrium? Forward and backward reaction rates are the same, and it's in that closed system. And we got our example of the Haber process here. Notice with this there is gas, gas, gas. So same state. Now you can have examples of this that are liquid, liquid, liquid. Okay, but this is gas, gas, gas. Now, if that's the case, it's a homogeneous equilibrium because the reactants and products are in the same state. The other version is when those reactants and products are in different states. Now these are all in different states, but even if you have one that's a different state to everything else, it's a heterogeneous equilibrium. And that's what we call it, hetero. Hetero meaning different, homo meaning the same. But we're not going to talk about heterogeneous equilibria. That is the next video. We're going to talk about calculations involving homogeneous equilibria. Now, Le Chatelier's principle, just a very quick reminder. This is the definition. You do need to understand it. You don't need to recall it as a definition, but you may as well, because at the end of the day, you need to understand it. And to do that, you need to have really read it and remembered it. So, a bit like this, position of equilibrium as a system changes to minimize the effect of any imposed changing conditions. So in my group, in my lessons, I always go, what if somebody punches you or pushes you? Okay, what would you do? Well, you push back, or if it's really violent, you might punch back, type of thing. Not encouraged though. Now, the fact is, if that happens, and we do it in the same way, but with chemistry, if a higher concentration is imposed, system will lower the concentration. And it will lower it to a certain level depending on that equilibrium position. And then the higher pressure is imposed, it will lower the pressure, and if a higher temperature is imposed, it will lower the temperature. Now, in other videos, we'll discuss how that happens, and through this, we'll talk about it as well. Now, the equilibrium constant, Kc, is worked out from a balanced equation like this. And you can see that it's products, Cd, over reactants. So products over reactants. Really important. The most common mistake is to get them mixed up. It's products divided by reactants. Now, if you then look there, you can see these coefficients, or the numbers before the balancing in the equation, are the powers you raise them to. Also, you'll notice that, like I said, CD is the product, AB is the reactants, and you also notice the square brackets. Square brackets mean concentration. So you can do concentration of gases and you can do concentration of liquids. So we're talking generally about liquids and gases. So if we then do this and we stop and say, here is the Haber process, I would like you to stop the video and turn it into that equation. So let's do it for you now. So Kc is equal to the product, which is NH3, and then we raise it to the power in the balanced equation, which is 2. And then we do N2, not raised to a power because it's not got a number in front of it. And then we do H2 raised to the power of 3. And that's our Kc equation. Now, this is really common in exams, so it's well worth practicing, okay? Just making sure you can always write this Kc equation. Now, if I give you an example, we can see all the numbers here, and that says at equilibrium. So at equilibrium, these concentrations were measured. So it's telling you this is at equilibrium, And that's what Kc is about. It's about the position of equilibrium. So we need to, therefore, just put the numbers into the equation. So stop the video and do it. Right. If we put the numbers in, okay, and here is your numbers. So your numbers are there, and you can see them here and here. And all I've done is copy the numbers over from there. Again, pause the video if you haven't done it already, and look at this connection. Now, I haven't actually done the units though. So the units are going to be like this. So if you look here, the units are all these, because their concentration is going to be moles per dm cubed. So we're just going to go equals there, because our Kc, and then we're just going to go moles dm cubed. And that moles dm cubed is for this one, and that's the unit of concentration, and it is squared. All I'm doing is copying this 2 down. And then I've got a moles per decimeter cubed for this one, and a moles per decimeter cubed for that one. So I'm going to put moles decimeter cubed, and then moles decimeter cubed again. Now, this one is raised to the power 3, so therefore I need to put 3. And now I've got my equation, but just in the units. So I've got to work out what the units are of Kc here. So I'm going to put the final unit here. If that is the case, and we then take this, well, we're going to cancel out our 2 at the top, because there's 2 of them. And then we've got 3 down here. So I'm going to cancel out that 3 and just leave behind the 1. So there's 1 here left. So basically 2 here, cancelled out 2 here, and I've got 2 left. Now if that is the case, I can rewrite it, okay, and I can rewrite it basically by taking the numbers and just kind of adding them together. So moles and moles, well that's 2 moles, so that's going to be moles to the power 2, and then I've got dm minus 3, dm minus 3, or dm minus 3 plus dm minus 3 is the minus 6. Now that is still the denominator. I need to make it the numerator. So if I'm going to do this and make it the numerator, it's like timesing by minus 1. Okay, so I need to times that all by minus 1. So if I times that by minus 1, I come over here and I say what the final thing is. Moles 2, okay, times by minus 1 is moles minus 2. So moles minus 2, and then decimeter minus 6 times by minus 1 is 6. Okay, so that's my final unit. So my final unit is this. Okay, and that will give me my mark in my exam. This will give me my mark in my exam. Really important. And very important, this or this will give me a mark in the exam. Okay, so don't not write this out. If you get it wrong, this will get you a mark, okay? Now the other thing is, just to finish off, is they normally like this, and they'll say this on mark schemes, with the positive one first. So it's this, they both will get you the mark, but if you're doing it absolutely 100% properly, we just reverse that, and you can see that this is correct and this is correct. So both are correct. And that is how you do a calculation, a simple calculation, using homogeneous equilibria and give the unit. So we're just going to go through another question just with the equilibrium amount. So this time you've got H2 and plus I2 going to HI. Notice they're all gases, so it's homogeneous equilibrium again. When the equilibrium has been established at 600 K, now I want to include this for 2 reasons. One is often they'll give you temperature in Kc equations, and it is pretty meaningless because you're not going to include temperature in your equation itself, but it can be there to put you off. So don't be worried if you see a temperature. Okay, and you've got equilibrium amounts, it means you use Kc, don't worry about it. Now, your equilibrium amounts are here, so we've got some nice equilibrium amounts, and then it says calculate a value for Kc at this temperature, write an expression, substitute the given values to calculate Kc, work out the units. Now we're going to talk about work out the units specifically in a minute, but what I'd like you to do, I'm going to move this to the side, I'm going to write this out in a second, stop the video, do the question. Okay. Right, so let's look at the question itself, and I'm just going to go straight for the Kc expression. So Kc, product is Hi, so the product goes on the top. It goes in the square brackets. You can see that it's got 2 by it, so it's squared. Right, we then go for the next one, and we go for our reactants. Okay, and our reactants You can see that they have no numbers by them, so that's our equilibrium. So if we're looking at this, we've already got 1 mark, okay? So we then go from here and we say, right, let's put those numbers in. So putting those numbers in is going to be, well, our product is 1.695 times 10 to the minus 2. Okay, so that is 1.695 times 10 to the minus 2. Okay, let's get rid of that. And we've got 1.65 times 10 to the minus 2, which is that one there. And then we know that that is, let's put it in the brackets, and we know that is squared. And then we go for that, and we've got the hydrogen first, 2.484 times 10 to the minus, so 2.484 times 10 to the minus 3. Okay, and then we've got 2.514. So that again is 2.514 times 10 to the minus 3. Okay, so we've put our numbers in, and that's all done. So from that point, all we do is put it into the, let me forget, there's a bracket. So we've got all that, okay, and that's going to go into our calculator. So if it goes into our calculator, what you will get is 46, and I'm going to put 46.0. We put that on to our calculator, but the important thing is not that, because that's pretty easy. You can just put the numbers into the calculator, that's all good. So we've done the expression, okay, we're going to get a mark for this, and we'll get a mark for that. But the fourth mark we're going to get is for our units. And this is the most important thing in this part of the video. You substituted the units, you got your Kc, so substitute your values, and you're going to work out the units. Well, the units is going to be moles per decimeter cubed squared divided by moles per decimeter cubed times moles per decimeter cubed. So moles per decimeter cubed times moles per decimeter cubed is squared. So you got squared at the top and you got squared at the bottom, which means they totally and utterly cancel, which means you don't get any units. Now, the most common problem is that people do this question and then they say there's no units, so they leave it blank, right? No, you have to show to the examiner that you understand that there are no units. So you have to say no units. You cannot just say blank or just leave it blank, because that shows no understanding, okay? So you have to actually say no units. I can't emphasize this enough. This is commonly missed. Don't miss it, okay? So no units. If you've got something like this and there's no units, you have to write no units. In our final question on this video, which is a slightly harder version where you have to calculate the concentrations, you can see we've got our equation here, and then we've got equilibrium amounts here. You can see it says moles, okay, and it does not say moles per decimeter cubed, which means you need to calculate the concentration. It gives you a total volume, so you can calculate the concentrations. The temperature is again irrelevant, and it gives you the equilibrium amount of your product. Now we want you to calculate Kc for this temperature, and you want the units. Now if you're happy to, stop the video, get on with the question. If not, I'll take you through the question. So let's put it to the side, and let's look at how we calculate the concentration. Well, concentration is moles divided by volume. That comes from the equation moles equals concentration times volume. So just dividing by the volume here, and it gives you your concentration. Let's move this down and then start writing out our equations. So all we do then is say, right, what's the first? What's Kc? Kc is going to be our products over reactants, so that's FeSCN. So we've got up here, and we've got 2 plus. And there's nothing in the equation, so that's that done. There's no numbers or anything. So then we go for our reactants, and our reactants is Fe3 plus, okay, and SCN minus. You can include the state symbols here if you want to do it full. I'm not here, but you can include the state symbols as well to give a full picture. Okay, so we've got that, and we've done our equation, and remember that's going to get us 1 mark in the exam, even if we don't understand the rest of the question. We then go here and we start putting in the numbers, and we know moles divided by volume is our concentration. So our product's moles is 0.05, the total volume is 5. So we can do this within the equation. We can just write it out within the equation. So what you can say is 0.05, and that's our moles, divided by our volume, which is 5. And we can just do that calculation. I encourage you to do that calculation in your calculator. Right, then we're now going to go for the Fe3+. The Fe3+ says 0.250. So 0.250, again divided by 5. We then got the SCN-. The SCN- is 0.150. So there's our 0.150. And then we put those all in our square brackets because the resultant number will be the concentration. So we've got that. So then we go down here. Now, at the end of all this, okay, when you put it in, we're going to put it to 3 significant figures, but the question might tell you how many units you have to use. Okay, but the final answer would be 6.67. So if you got 6.67, well done. Okay, and then we also have got to do the units. So we've got a moles per decimetre cubed up here, a moles per decimetre cubed down here. Those will both cancel. That will leave you a moles per decimetre cubed at the bottom. If that's a moles per decimetre cubed at the bottom, we have to times it by -1 to get up to top. So that would be either moles -1 decimeters 3. So you could write it like that if you want. Or proper answer would be the positive one first. So decimeters moles -1. Okay. So there you have a calculation where you are given the moles, you have to calculate the concentration, and you're given the units and your answer to 3 sig fig.